Welcome back to our journey through the math of machine learning. Last time, we talked about those perfect bowl-shaped cost functions. Well, today, we're getting our hands dirty with gradient descent. This is the algorithm that actually finds the bottom of that bowl. It is, no exaggeration, the engine that powers almost all of modern machine learning.
So here's our game plan. We'll start with the big idea, then get into the math behind it. We'll look at something called the learning rate, which is absolutely critical. Then we'll explore the three main ways to get down the mountain, and finally, we'll see why this one algorithm is such a huge deal for AI.
All right, let's kick things off with the main goal here. In machine learning, right, we want our models to be as accurate as they can possibly be. And we measure that with a cost function. A lower score is a better model. So the whole quest is about finding the absolute lowest point, the minimum cost.
Okay, so we know models learn by trying to make that cost function as low as possible. But how? I mean, how do they actually do it? It's not like they can just look at the whole landscape of possible errors and pick the lowest point. The actual process is way more clever, and it's all about taking one step at a time.
This analogy is just perfect. Picture it. You're standing on a huge, complex mountain, but it's completely covered in fog. This mountain represents all the possible errors your model could make. Your goal is to get to the very bottom, the valley floor, where the error is lowest. What do? You can't see anything, so you just feel the ground right where you are, find which way is steepest downhill, and you take a small step. Then you do it again, and again, and again. That right there is the core idea of gradient descent.
So let's take that simple idea of our foggy mountain climber and translate it into the language of math, the language a computer can actually understand and execute.
The algorithm is actually beautiful in its simplicity. It's really just these 4 steps, over and over. You start at some random spot on that mountain, you figure out which direction is down, you take one step, and you just repeat that loop until you can't go any lower. That's it!
So, the big question is, how does the model feel the slope? Well, it uses this incredible mathematical tool called the gradient. You can think of the gradient as a vector. Basically, it's an arrow that tells you 2 things: which direction is the steepest uphill climb and how steep it is. It's our compass on this foggy mountain.
And this little formula right here is how we use that compass. See, if the gradient points uphill, all we have to do is go in the exact opposite direction to go downhill. We take our model's current parameters, that's the W, and we update them by subtracting the gradient. That minus sign is everything. It's what makes us go down instead of up. Now, what about that little alpha symbol? Oh, we're definitely getting to that next. It is super important.
Okay, time to talk about that alpha symbol. This is called the learning rate, and it basically controls how big of a step our mountain climber takes. And let me tell you, getting this value right is absolutely crucial to success.
The learning rate is what we call a hyperparameter, which is just a fancy way of saying it's a setting that we have to choose before the training even starts. Think of it like a knob you can tune. Are you going to take tiny, careful baby steps down the mountain, or are you going to take huge, confident leaps? That's what alpha decides.
And here's the catch, the big trade-off. If your steps are too small, sure, you'll get to the bottom, eventually, but it could take an unbelievably long time. On the other hand, if your steps are too big, you might literally jump right over the valley and land on the other side. Then you'll jump back and keep overshooting, bouncing back and forth forever without ever actually finding that lowest point.
But here is the really cool part. For those simple, bowl-shaped, convex problems we talked about in the last explainer, this whole process is basically foolproof. As long as your learning rate isn't ridiculously high, gradient descent comes with a mathematical guarantee that it will find the one and only global minimum. It's not a guess, it's a certainty. It will always find the bottom of the bowl.
All right, now things start to get a little more nuanced. It turns out there isn't just one single way to walk down this mountain. The strategy you use can change, and it all depends on how much data you look at before deciding where to take your next step.
This table lays out the 3 main flavors. First, you've got batch gradient descent. This one is super careful. It looks at the entire data set to calculate the perfect direction for a single step. It's slow, but its path is really smooth. Then you have stochastic, which is the total opposite. It looks at just one single random data point and takes a step. It's incredibly fast, but the path it takes is really noisy and zigzags all over the place. And then there's mini batch, which is the perfect compromise, looking at a small group of data points at a time.
The key difference here is really about how often the model gets to update its parameters.
During one epoch, which is just one full pass over all our data, batch GD updates only once. Stochastic, on the other hand, updates after every single example. And many-batch, as you can see, hits that sweet spot right in the middle.
So, which one do people actually use in the real world? Well, as you can see here, it's not even close. Many-batch gradient descent is the overwhelming champion. It's pretty much the standard default choice for training almost any modern, large-scale AI model you can think of.
And what's its secret? Why is it so dominant? Well, it's because its structure is a perfect match for modern computer hardware. The whole idea of processing data in these small, manageable chunks, these mini-batches, is exactly how things like GPUs are designed to work. It lets us tap into all that parallel computing power and makes training unbelievably fast. So let's just take a step back for a second. We've seen how it works, but let's talk about why this one single concept is so ridiculously important to the entire field of AI.
It really comes down to three things. First, it's universal. You can use it to optimize pretty much any model you can imagine, as long as you can calculate its gradients. Second, scalability. When you're dealing with the massive data sets of today, with billions of data points, gradient descent is really the only game in town. And third, it's the foundation. All of the more advanced, cutting-edge optimizers you hear about, like Atom or RMS-Prop, they're all just clever variations on this core idea. I absolutely love this quote. It's like a GPS for learning. Think about it. Your GPS doesn't need a map of the entire planet to work. It just needs to know where you are right now and which direction to go next. That's gradient descent. It doesn't need to see the whole error landscape. It just needs its compass, the gradient, to tell it which way is down, right from where it's standing.
Okay, so we've done it. We've used our GPS, we've followed the slope, and we've made our way to the bottom of the valley. But believe it or not, our journey to truly understand our model isn't quite over yet. And this leads us to a really, really important final question. Our GPS, gradient descent, is fantastic at navigating the landscape we give it. But what if the landscape itself is wrong? What if our model and the error surface it creates is based on assumptions about the world that just aren't true?
And that is exactly where we're going in the next explainer. We're going to dive deep into the fundamental assumptions behind a model like linear regression and explore what happens to our performance when the real world doesn't play by our model's rules. I'll see you then.